Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, good morning, everyone. It's my pleasure to welcome Svetlana Lazebnik from the University of North Carolina, Chapel Hill, to give us a talk this morning about her research. Lana got her PhD last year from the University of Illinois, actually 2 years ago, right? University of Illinois, Urbana-Champaign, supervised by Jean Ponce and Cordelia Schmidt. She's one of the world's leading experts on object recognition, and I think you'll find today's talk quite interesting and see the connections to the work we're doing here on photosynth.
Thanks, Rick. So I will talk about some of the projects I started this year since moving to UNC, and the main theme is modeling and organizing large-scale internet photo collections. So, in the last few years, many computer vision researchers have become fascinated by photo sharing websites like Flickr. So there's a lot of websites out there. Flickr is the one I know the best and the one that gets used the most in published literature. So I personally have a Flickr account. I put my pictures on there, and I spend a fair amount of time just sort of browsing and playing around with it. So here are some numbers that are I think current as of the end of 2007. So Flickr is very large in terms of the number of images, the number of users, the volume of images that gets uploaded daily. I think now they also are beginning to allow short video clips, and there's a very rich tag data that goes along with the images. There's geotagging and so on and so forth. So it's a very sort of rich and interesting test bed. So from my personal experience of playing around with the Flickr interface and just trying to learn about what kinds of pictures are out there, it's very often frustrating. So the main thing that users do, or at least the main thing that I do when interacting with Flickr, is basically do keyword searches. So here's a very simple example. I do a keyword search for Apple just to try to find out what comes up. What is the universe of Apple images like? And here is pretty much the best way that you can get a summary of the results in Flickr, as far as I know. You basically display thumbnails of the most relevant search results. The most interesting search results kind of give you very bizarre pictures that might not be apples at all. And most recent, obviously, is not a very representative sample. So most relevant is about the best you can do there. And you can see that, well, there are a few images that are unquestionably apples, like this one over here. Then there's images having to do with Apple computers and Apple brand products. So you can see that there's a kind of polysemy going on. So Apple obviously has two dominant meanings. But then even in these top 24 results, there's a lot of garbage. There's images that might somehow, if you look up close, be relevant to one or the other sense of Apple. But this is not really the first kind of search result that you want to see. They're just not very salient. Here's another example for Statue of Liberty. So here in the top 24, we get a lot of salient results. At a glance, we can see fairly easily what the Statue of Liberty looks like. But once again, even among the top 6 most relevant images retrieved, in 5 of them, you can hardly see the statue at all. And also many of the results in this top page, and this was retrieved maybe a couple of days ago, are basically from the same user. So in the second row, like 3 of the middle images are from the same user, Scan D Blue. And here's some more from the same user. So we're getting basically a lot of very similar images. Instead, it would be much better to see sort of different salient aspects of the Statue of Liberty, or images that look very similar when taken by a variety of users. So we want to see a more representative slice as opposed to just, one user's pictures being overrepresented on this page. And also from this page, it's hard to get a sense of, well, is there just one unique Statue of Liberty, or are there several copies of these statues in different parts of the world? Because if there are, and you will see later that there are, this is something we want to be able to see up front. So, from these results, it's easy to see what the Statue of Liberty looks like, but you don't know if this is all there is to the Statue of Liberty. Are there other interesting views? Are there other statues? This is not necessarily complete. And of course, the top 5 images, or 5 of the top 6 are kind of garbage. So this is what comes up again and again. When interacting with Flickr, their interface is so simple that it's just very hard, and not just with these queries, any kind of query you want to issue, it's very hard to get a complete, at a glance summary of what does a given category look like. What are all the relevant themes or motifs or iconic images for a given category? So this is what we want to do. This is what I will talk about here. Starting with a large noisy pool of photographs basically downloaded by issuing a query search, such as for Statue of Liberty or Apple. First of all, we want to sort out the good pictures from the bad pictures. So which pictures really do represent the concept of interest, and which ones are just noisily tagged or just spurious. And secondly, we want to very compactly summarize the set of relevant images. So we want to find iconic images that are somehow especially representative or especially salient of the subset of the good subset of the query results. And these two problems are actually very interrelated. So finding iconic images, my second point here, can actually help to do the first. So it's not necessarily that first we have to sort the good images from the bad images and then cluster the good ones to get iconic images. We can actually start by somehow getting iconic images, and that will help us to determine what are the other good images for the category. So these two problems are really very tightly interrelated. So how exactly can we define an iconic image? So there is no unique answer to this, and let me just show briefly what people have done with this concept in the literature. So one of the first places where you see this idea of iconic or canonical image mentioned is psychology literature. And in the psychology literature, the work by Palmer et al., they are concerned, or were concerned mainly about basically single rigid 3D objects. If I give you a picture of a toy horse or of a telephone or of some common object, what are sort of the aspects of that object that you recognize the most easily, that you think are the most characteristic? So this is what the kinds of questions that psychology literature has tried to answer. So this aspect of the horse might be relatively easy to recognize and relatively characteristic, as opposed to, let's say, a view of this horse from the top or from the back. So there are certain views of 3D objects that people just like to imagine better and find easier to recognize than others, maybe less common or less bizarre views, or more bizarre views. So in the computer vision literature, people have tried to quantify these ideas. Once again, given a known 3D model, how can we compute some sort of common or representative views? Or instead of a 3D model, we can also try to do that with a large set of pictures taken around the viewing sphere of an object. How can we find a subset of views that represent it? More recently, people have looked at iconic or canonical images for products and logos, obviously kinds of imagery that has commercial significance. And that is not too difficult to do, because images of products and logos tend to be fairly simple and stylized. The kinds of product images you tend to search for on the web, would have a very large picture of the product of interest with relatively little clutter and so on. So in this case, a canonical image would be an image that basically has as little clutter as possible and that is similar to many other images. So if you're looking for images, let's say with the Apple logo, you can use local features to cluster images, all of which contain the Apple logo, and then find the iconic image that basically has the most matches to all the other images. And for example, the fewest non-matching features. So it would be the image that has the most salient instance of this logo that also occurs in a lot of other images. So people have also tried to extend essentially the same ideas to landmarks like Statue of Liberty, Eiffel Tower, and so on. So a lack of clutter, having a very salient representation of the landmark of interest that takes up most of the image that maybe is not occluded, that has a lot of features that can match to other images of the landmark. This is how an iconic image for landmarks can be characterized. So in some work, for example, Berg and Forsyth, who were, I think, one of the first to look at iconic images for landmarks, this is their key criterion. This is an image that has a clearly delineated instance of the object, and the way that iconic images are found in this work is by trying to find the foreground-background separation, basically to isolate the foreground that contains the object and to look for images that have a lot of this, salient foreground. And another work from Ian Simon at UW, canonical images for landmarks are defined in terms of basically 3D structure. So like landmarks is just an instance of these single 3D objects, so it's a unique object in the world. So it's characterized by a rigid 3D geometry, so we can apply essentially many of the ideas that people have used for single 3D objects to deal with landmarks. So 3D geometry, distribution of viewpoints in space, plays a very large role. And finally, there's another category of categories, or a category of visual classes that hasn't been looked at a lot, but that actually intrigues me. So general categories, not single 3D objects, not products, not landmarks, more or less abstract categories. Let's say love, beauty, things like that. Does an iconic image exist for such a category? And for these kinds of categories, 3D geometry is no longer meaningful. Even foreground-background separation is not necessarily meaningful as it is for products and landmarks, because the whole image, like this image of a rose, might somehow represent love. And there's no point in trying to distinguish foreground from background because it's not a concrete concept. So this is something on which there hasn't been a lot of work. But this is kind of an overview of the kinds of criteria that people have used to find iconic images. Okay, so in my talk I will deal with two kinds of imagery. One is landmark collections, Statue of Liberty, etc. And for this, the viewpoint we take in our work is very much in line with the photosynth work, is very much in line with the UW photo collection summarization work, is that 3D geometry, multi-view geometry, is really the most important cue that we can use to deal with landmark image collections. So other work on landmarks that tries to view them essentially as 2D images, let's say just using SIFT feature matching or bags of features in 2D, in our opinion, is just not strong enough. We really do need to bring in multi-view geometry. We need to bring in strong 3D geometric constraints to recognize successfully landmark images and to find out which images are representative. So which images, for example, come from a tight cluster of similar 3D viewpoints in the world. So this is very much a 3D approach and not just a 2D image clustering approach. However, enforcing 3D geometric relations is very computationally expensive. Extracting features, doing ransack between every pair of images to estimate homographies or fundamental matrices, etc. If you do this for every pair of images, it's quadratic in the size of the collection, so it's not very scalable. So enforcing 3D geometric constraints and figuring out the 3D relationships between images is not very scalable. So what we want to do is start by 2D image clustering, to sort of pre-process the image collection and to group images that are already very likely to come from similar viewpoints. So even though we completely believe in 3D geometry for landmarks, we want to start with fast 2D image clustering, and I will explain in more detail to make this more scalable. And finally, summarization, as in Ian Simon's work, has been done very successfully as basically a byproduct of reconstruction of estimation of all the 3D geometric relationships. If you start by estimating all the 3D points from the landmark in the world and all the camera viewpoints from your image collection, you can then cluster more or less these viewpoints to get iconic images as the centers of clusters. But for that, it requires that we perform all the reconstruction and all the pairwise geometric matching first, and that takes a lot of time. So we actually take the opposite approach of doing summarization first, quickly, to give us a good initial guess for the 3D structure of the world. So we kind of invert the process. We do summarization first, and out of that, 3D reconstruction also more or less falls out. And in the second part of the talk, I will talk a little bit about this general category question. How can we deal with just categories like love, beauty, and so on? So here, we don't have a lot to go on, no 3D geometry or anything. So as you will see in that part of the talk, we have to rely on semantics a lot more as captured by image tags. Okay, any questions so far? All right, so let me talk then about our work on landmark image collections, and that will appear in ECCV this fall. So we start with our large collection. Typical size would be about 50,000 images, although we could in principle download a lot more. And typically 40 to 60% of this initial collection obtained through keyword search on Flickr is noise. So if we search for Statue of Liberty, 40 to 60%, I don't remember the exact number for the data set, are images that don't have the Statue of Liberty in them at all. So it's a very sort of noisy data set. And as a first step, we perform clustering using 2D global image descriptors to just find images that look almost the same in 2D, that pixel by pixel look more or less the same. And the idea is, if these images are so similar, most likely they come from very similar viewpoints anyway. So we do this clustering, followed by some geometric verification to make sure that these images really do come from the same viewpoint, to get a much smaller subset of these representative images from clusters or iconic images. So we go from about 50,000 images to maybe a couple of hundred of these iconic images following this clustering stage.
Do the iconic images have to have multiple things mapped to an image, or can you have single things?
Sorry?
Your iconic images are images that are clustered together because they appear similar enough. Can you have clusters of size 1, or do you have to have a certain minimum?
Well, in practice, we have, I think the threshold is about 8. I will show in a couple of slides exactly how we do this geometric verification, but in order to be able to do the verification, we have, some sort of minimum size, and 8 is what we use. Okay, so we have these iconic images, and next we want to figure out what are the viewpoint relationships between them. So we match every pair of iconic images and try to estimate the epipolar geometry between them to figure out how their aspects relate to one another. And then we go from just this pile of iconic images to a graph where edges represent two view relationships. And we cut this graph basically to find groups of images that see more or less the same features of the landmark. And from these components, we can perform, for example, 3D reconstruction. So these components allow us to perform reconstruction very efficiently because they would be a lot smaller than the whole graph, as I will explain. But also we can use these components as a natural browsing structure for the landmarks, as I will also explain. So this is kind of a brief overview of the approach. And now let me give you more of the details of every step. So the first step of appearance-based clustering, basically this is one of the end results of the step, and you can see the kinds of images it looks for. Images that almost pixel per pixel are the same. So for this, we use so-called gist descriptors that were developed by Odd Alava and Antonio Torralba and have been popularized in recent years in graphics and in vision literature by Alyosha Efros. So here you can see on the left is just some generic image of a forest, and on the right is a synthetic image that has the same gist descriptor as this forest. And you can see that this gist descriptor captures sort of the coarse texture characteristics of the image. The main, sort of directionality of textures, where are the various blobs or strong edges in the image, and so on. And this gist descriptor is about 1,000 dimensional, and it's obtained from taking a steerable filter transform of the image and then summing the filter responses over very large areas, different more or less quadrants of the image. And this is the kind of information that it captures. So it turns out by extracting these gist descriptors from the entire image and doing k-means clustering on them, is fairly successful in finding groups of very similar looking images. But of course, we can't trust just the output of the gist. So in fact, in this example here, you can see there's one outlier. There's one image that doesn't really match the others, but got clustered with them anyway. So we really have to make sure that this kind of thing doesn't happen. So we can't just trust gist alone. After we do this gist clustering, we have to go to every cluster and make sure that the cluster does represent a set of images that are geometrically consistent, that have the same sets of features viewed from more or less the same viewpoint. So for this, we take the top few representatives from each cluster, meaning the images that are closest to the center of the cluster, and we use 8 in the implementation. So we take the top 8 images closest to the center and perform pairwise matching between them. So we extract SIFT features and then do ransack to estimate either a fundamental matrix or a homography, depending on the relationship between the images. And then the number of inliers to this relationship tells us basically, are these images geometrically consistent or not? And then among these top 8 images, we simply sum up all the inliers they get by being matched to the remaining images. And the image that gets the most inliers is declared as the iconic image for the cluster. And there's also a threshold on this total sum of inliers, so that if there are too few among the top 8 images, we can see that the cluster is not geometrically consistent and throw it out. And empirically, we have found that this is basically sufficient. Even if you have a very large cluster, you only take a top very few representatives and do this matching. It really pretty much tells you everything you need to know about the cluster. And I will show later we have quantitative evaluation of this in terms of recall precision curves. So after verifying each cluster and keeping the representatives or the iconic images from the geometrically consistent clusters, we might get a set of images that looks like this. So these would be our iconic images. And we can see that among them, there are some that still look almost the same, like a few of these images on top. And a few of the other ones, clearly there's been some over-clustering. There's been some over-segmentation. Because this gist clustering is far from perfect, some images that really could have been clustered together didn't get clustered together, and so on. And there are some images that still represent almost the same viewpoint but don't look the same in 2D, either because of clutter, like a person standing in front of one of the images, or maybe the lighting is too different, or maybe there's too much camera zoom or viewpoint change for gist to work. So now we have to fix all this. Now we have to basically verify the geometric relationships between iconic images. So we match every pair of iconic images to each other, once again, to see whether or not there's a two-view relationship between them. And this gives us the graph structure. This gives us a so-called iconic scene graph, where the nodes are these iconic images representing their clusters, and the edges represent either homographies or fundamental matrices, and the edges are also weighted by the number of inliers to this transformation. So this graph basically, and unfortunately these graphs have been pretty hard to visualize. So here you can kind of see an attempt to visualize the graph. And there are two types of edges. I don't remember. One of them is homography and the other one is fundamental matrix. And nodes are images. So this is what the graphs tend to look like. They look fairly messy. But one thing you will usually find in them, they have sort of very tight clumps. They have very tight clumps representing sort of very popular views, like the frontal view of the Statue of Liberty, and maybe they have several, if there are several dominant aspects. And then there might be a lot of sort of weakly connected components or isolated nodes floating about. So we have to analyze this connectivity. So first of all, with isolated nodes, because we've already tried to estimate the geometric relationships between iconic images, we have an idea that if there's an isolated node in the graph, it doesn't match anything else. So this is already a pretty strong hint that, this might be garbage. This might be a set of images that doesn't truly belong with the landmark and should be thrown out. So for this, this is the only place where we use tags for our work on landmarks. We'll look at isolated nodes and try to match their tag distribution to the distribution of the tags for the largest graph components. Because the tags, the most popular tags associated with the largest graph component, we have a pretty good idea that this is really a very good sample of tags that describe the landmark well. So by taking the tags from the isolated nodes and seeing if they appear in this list, we can basically quickly check are the tags associated with this isolated node garbage or not. And this gives us a filter that we can use to basically eliminate a lot of these isolated nodes. Because what we have found is that there will be a few sort of sets of near duplicates in the data set. Just very, very similar images that were all taken by the same person and just somehow spuriously tagged. So most of their tags are garbage, and we can recognize that pretty easily. So this is just a filtering step to clean up some of these stray graph nodes. But what we're really interested in are the tightly connected components of the graph, because this gives us the most salient characteristic aspects of the landmarks. So what we do is we have our graph that has this sort of loose structure with a few clumps, and we run normalized cuts to get these clumps or these tightly connected subgraphs, which really end up corresponding to very similar aspects. So I will show the Statue of Liberty results in a little bit. But then what we can do with these components is we can use them for structure from motion. So basically, one of the big reasons to work on components as opposed to the whole graph is that they're much smaller, so structure from motion can be done, especially global bundle adjustment, can be done much more efficiently on subgraphs as opposed to on the whole graph. So we basically process each component separately. So we use the graph structure. We find a maximum weight spanning tree where the weights, if you will recall, are given by the number of inliers. So obviously, to incorporate images into the model, we want to go by images that have a lot of inliers to other images. So we use a maximum weight spanning tree to determine the order of incorporating images into the 3D model. And finally, we don't forget about the connections between the components. It could be that there were a few weak connections that were cut when we did the normalized cuts, and we don't throw those out. In the end, when we separately reconstruct each component, we can go back to the cut edges and use the matches along those edges to merge the component models. And finally, so this, when we reconstruct each component and do as much merging as we can, this gives us a good 3D sort of photosynth style representation of the landmark. And it's built using relatively few images, so it only uses the iconic images. So if we started with 50,000 images, maybe half of which actually contained the landmark, at this point, we only end up with a model that uses a couple of hundred iconic images. But we can fix that. We can enlarge the models by registering additional non-iconic images. And this is very easy to do. So let me show you a video that kind of shows some of the models that we get. So unfortunately, I don't have the models in VRML format, but in this video, you can see we have 3 data sets. So this is Statue of Liberty. And here's sort of a brief screenshot of how merging works. These are different aspects of the Statue of Liberty that still have a lot of overlap, so they can be merged. And this merging, the matching, and the estimation, this is all automatic based on the graph structure. So this is a bigger merged Statue of Liberty. And you can see there are a few outliers, so we haven't done a lot to make our models perfect. And this is our second data set, San Marco, Piazza San Marco in Venice. So this is a big component that includes the front of the cathedral. And the third data set is Notre Dame in Paris. So that was a dominant model. And this is the model of the back of Notre Dame, which is hard to merge with the front. So this kind of gives you the sense of the 3D models that we get using our approach. So there are a few outliers. And we really have done a lot less, to sort of cosmetically clean up the models and make sure that there are no outliers, no incorrect matches, and so on. But you get the idea that, by and large, the structure found by our algorithm is pretty much correct.
So did you, as you're pre-clustering the things that have similar views, did you find that there sometimes wasn't enough baseline for structure for motion reconstruction?
So within a cluster, there's not a lot of baseline. But between clusters, because when we match the iconic images basically to each other, this is where we get the baseline most of the time, from different iconic images. And even there, there's a good number of homographies among those as well. So there isn't, always sort of, in some cases it's true that it's hard to get a wide baseline, but overall, I think the biggest problem still remains is when the baseline is too wide and you can't merge things. So I think that is kind of a bigger problem for us than not having enough images with a good baseline. So this is 3D reconstruction, and it shows what we can do with the iconic images. That the iconic images basically have enough information in them to permit the 3D reconstruction of the landmarks. And the second thing, besides reconstruction, that the iconic images allow us to do is browse the collection. So we have a 3-level browsing structure. So at the first level, we have the different components that we obtain by partitioning the iconic scene graph. So each component includes a number of iconic images. So here we expand one component, and these are just the iconic images from that single component. And you can see that these are images that some of them look very close to each other, even in 2D, so it's almost identical aspect, but others include a lot of zoom, sort of viewpoint change, and so on, but there's still a lot of overlap in terms of visibility, in terms of what all of these images can see. So the components represent sort of different iconic images that still see more or less the same part of the landmark. And then we can expand each iconic image to get a cluster that was obtained originally by gist clustering, and that all contains images that are almost the same as the iconic. So this is a 3-level browsing structure for the data set. And I can show an example. Yes?
So in that, you go back to the slide. So I'm surprised, like the image with the sunset in it. Mm-hmm. I'm surprised that you got enough features on the Statue of Liberty there at all to pass any sort of geometric verification.
Yeah.
How did that?
Well, I mean,
how
it's
did that pass? Like,
features. Well, we work with a reasonably high resolution image, so it's 1,000 by whatever. But there wouldn't be a whole lot of features there.
Right.
So
I'm talking about
I mean,
the second to last column, third one down.
Like this one.
That one.
Yeah. So, I mean, I can't 100% guarantee that all of them are absolutely correct, but I think there's still enough maybe features around sort of the outline. And our threshold for the number of inliers, I think, was reasonably low, like maybe 15 or so. So it's possible you can get 15 or so features out of this. But in general, and using even higher resolution images, I think, would help even more. So it was kind of a compromise. If you use the original resolution images, you can spend forever extracting SIFT features and doing the matching and so on. But on the other hand, if you go to lower resolution, then you can lose images like that. So we haven't, completely found the right trade-off. So I think we use the 1024 by whatever resolution on Flickr. So. But I'll show a little later, it's true that getting enough features for the Statue of Liberty was sometimes problematic. But let me show examples of browsing for Statue of Liberty. So this is level 1, where we have all the different components of the statue. So this, for example, is the face of the statue, which is kept in the museum or something. So you can see that, these are all the images in the same gist cluster.
So I have a question about that.
Mm-hmm.
Because the original gist cluster gives you a lot of garbage, but at this point you've only filtered out the geometric.
Yeah, so actually one thing I forgot to mention is that these are already filtered gist clusters. So the garbage, once we decide what the iconic image is for the cluster, it's relatively quick to take every other image and to verify it geometrically against the iconic. And it's, obviously it's much quicker than doing pairwise verification of the whole cluster of every image to each other. So what we do instead is we first do pairwise verification of the top 8, decide on the iconic, and then just verify every remaining image against the iconic. So that's basically linear in the number of images in the cluster. So what you see here is the clusters that have already been cleaned up by throwing out all images that don't match the iconic. So the biggest component is what you've already seen, is the more or less frontal view of the statue. So, and these gist clusters following verification are really very clean. There's almost no mistakes in them. And in fact, the second component for the Statue of Liberty, the second largest connected subset of the graph is actually Las Vegas. So this is the Statue of Liberty in Las Vegas. So you can see that all of these images have the same sort of distinctive background, and it's probably this background to a large extent that enables us to, connect all these images together and to recognize this Las Vegas component. This is a nighttime Las Vegas component. So sometimes we get lucky and we can match night views to day views, but most of the time they're too different, both for gist and for SIFT features. So we really end up with different components for night and day. And then there's also a third component for Tokyo. So we get a pretty large component for a Statue of Liberty in Tokyo. And once again, the background is distinctive enough so we can distinguish it. There's a nighttime Tokyo component. So you get the idea of what the results are like. And I think there's one component that basically is incorrect. So this is a component that doesn't truly have the Statue of Liberty. But these tags, so I mentioned that we try to use some tag-based filtering to remove isolated components. But oftentimes the tags are not informative enough. So New York City are very common tags for the Statue of Liberty, so we just don't have enough information to throw this out. So this gives you an idea of what, what kind of browsing this iconic scene graph enables. Yes?
Statue of Liberty in Seattle.
There's one in Seattle?
Alki Beach.
Oh, really? Okay, yeah, so I know there's one in Paris, and that one hasn't shown up either, but that one is kind of hard to photograph. You can't really get up close to it. So I don't actually know, I haven't gone to the data set and seen how many images of the Statue of Liberty in Paris there are. So there might be a few more, like in Seattle or wherever else, that just don't show up. And you also have to keep in mind that our approach is based on clustering. So it's pretty brute force, and it looks for modes, basically, for very large clumps of images. So if you have only a few images of the Statue of Liberty in Seattle or the one in Paris, we might end up just losing them. So this is one sort of disadvantage of this clustering-based approach. It's very good at finding like the very salient and dominant components, but it might throw out a lot of smaller components that could still be very interesting. Yes?
So when you were doing your structure for motion reconstruction, in the very first step when you were doing it independently in each cluster, did you find that like certain clusters didn't have enough parallax or too small baselines?
So we're reconstructing components. I think Rick asked a similar question. So if you look at the images inside of a component, let's see. If you look at the images inside of a component, like this whole collection, I think there's enough parallax between them to be able to do a good job. And, some homographies are also usable for reconstruction. You can use information about camera rotation and so on. So overall, we're okay. So we don't try to reconstruct individual clusters. When we deal with sufficiently large components, it works out fine. And, sometimes if the component is too small, you might get a reconstruction that's not very interesting. So here in Tokyo, you kind of get the idea that there's a statue in front and there's a bunch of stuff in the back. But I don't know how interesting this reconstruction really is. And this is still not a completely bad case. So you could get an even more uninformative component, let's say a very distant view of the Statue of Liberty, like a view from top of Empire State Building or something, that basically just shows the New York skyline. So from that, you basically get a trivial reconstruction. So, we can get reconstructions, but they're not always going to be good. There's going to be bad cases. But for, the good cases, like the central aspect of the Statue of Liberty, we don't have that problem. Okay. And, we have tried to quantify basically our various filtering strategies. does, for example, starting with gist clustering and then performing geometric verification and so on, does it improve recall and precision? So it definitely improves precision, and recall basically in every filtering stage goes down a bit because we end up rejecting some things. Things that are not geometrically verified, let's say to the iconic image, get thrown out, and sometimes we make a mistake. So in every stage, we reject some images, and the recall goes down a bit, but the precision stays pretty high. So for the Statue of Liberty, in the end, we're able to register about half of all the images that actually contain the Statue of Liberty in them with pretty high precision. And also we've tested how good is the set of iconic images for basically testing or trying to recognize the landmark in new images. So we take a never before seen image and we try to figure out, is there a Statue of Liberty in that image using just our iconic images. And we can either do k nearest neighbor matching of this test image to the iconics using gist, or we can use a bag of local features matching with a vocabulary tree and follow that by geometric verification. So very basic registration approach. And one thing that's interesting about the Statue of Liberty is the vocabulary tree itself. So it's hard to see, but basically if we do just nearest neighbor matching using a vocabulary tree, this is the recall precision curve we get, this red curve. And it's basically random. So if we try to do bag of features matching to the nearest iconic, for the Statue of Liberty, it pretty much fails miserably. And this has to do with the fact that it's hard to get a lot of inliers for the Statue of Liberty. It's not very textured, so we don't have a lot of local features, so that's going to fail. And actually gist, so just global 2D matching, works a lot better than the vocabulary tree for this case. So this is just one interesting note. Okay, so basically we get similar kinds of results for Notre Dame, which is smaller, and for Piazza San Marco. So one interesting note I want to make about this one is the merging. So we get models basically for the front of the square with the church and the back of the square, and there's also this tower. And we've tried really hard to merge the two, and we just haven't succeeded. And, you know, there are a few sort of difficulties. One of the difficulties is the tower. So this tower, this clock tower is completely symmetric from all four sides. And there's a lot of images in which you just see the tower against the sky and nothing else. And for those images, it's basically, you know, very hard to get the correct camera pose. What we end up is, you know, with a camera pose that basically has like a fourfold ambiguity. And so when you have a bunch of misestimated cameras for the pictures looking at the tower, and you try to do some merging with that, it basically can completely screw things up. It, you know, puts the square together backwards where, you know, walls intersect and so on and so forth. You know, so it can be tricky. And once again, this clustering-based approach, it, you know, keeps the dominant aspects, and sometimes it just throws out a lot of the things in the middle, which in this case turned out a lot of times to be the missing links. There might not be a lot of pictures that really see both aspects together and that can help you to do the merging. So this is one weakness of this clustering-based approach that we're going to work to address. Okay, so basically this is all for this part of the talk, and I can go into the second part just a little bit. Does anybody have any questions? Okay, so I will briefly talk about the second part, which was actually presented last week at the Internet Vision Workshop. And this part is more sort of speculative and open-ended. So what I wanted to see is what I mentioned in the beginning: what can we do basically with just abstract categories? Can we find any useful summaries at all? And So basically, one of the things we may want to discover is in the apple example is the fact that there's Apple the fruit and Apple the computer company. As far as even more abstract terms like beauty, the best we can hope to discover is basically distinct themes. That, women may be beautiful, sunsets may be beautiful, flowers may be beautiful, and cats may be beautiful, but in slightly different ways. So we want to find different semantic subcategories or sort of instantiations of what an abstract term could mean. So here, basically, we also have this recall versus precision problem. Ideally, we would like to find all images that somehow represent love or beauty, but it's much harder to define than in the case of Statue of Liberty. In the case of Statue of Liberty, we could have ground truth. Does this image show the Statue of Liberty or not? And we could have people actually annotate images with yes or no, whether or not it shows the Statue of Liberty. For these kind of categories, it's no longer possible. We can't have a person look at any of these given images and say, does this image represent love? So we have to kind of throw out the whole question of recall out the window. We don't really have the hope of retrieving all of the images out of a large noisy collection that represent love. But what we can do is maybe find a few subsets of the images that are internally consistent, that correspond to some recurring visual motifs. Like, hearts or roses will be very typical for love. We don't know about a whole bunch of other images, but we find a few clusters about which we can say, yes, these are representative images for this abstract term. So, it's hard to define what iconic image means in this case because it's so sort of speculative, but the working definition we came up with is an iconic image basically is a good-looking representative of a group of images that look the same and have similar semantics. So this really has three components. One, appearance, images have to look the same. Two, semantics, they have to all be roses or all be hearts or all be rings. And the third, they have to be good looking. And we're not sure why they have to be good looking, but it can't hurt. So this pretty much dictates the algorithm. So we want to find, perform joint clustering to find groups of images that are consistent using both appearance descriptors and flicker tags. And secondly, for each cluster we pick a representative iconic images by doing automatic quality-based ranking. So our joint clustering is very simple. We do first clustering with GIST, just like in the landmark work. And that, does ensure some uniformity in appearance, but it doesn't ensure uniformity in semantics. So here we have a bunch of round structures, but some of them are apples, some of them are apple pies, some of them are, iPod buttons. So, and some of them are actually apple pies with the Apple logo in the middle. So appearance gets us somewhere, but we still have this mishmash of different themes. So for this, we try to capture semantics by clustering tags, and we use a very simple approach. We run so-called probabilistic latent semantic analysis to transform the tags into a latent topic space, and then we cluster the topic vectors with k-means. And this gives us a bunch of semantic themes, and we simply intersect the two clusterings. And then, this is an actual sort of snippet out of the results that we get. So this is a hand-picked snippet, so, this shows where it works nicely, but we didn't make it up. Yes?
Just a question. I thought you were doing just a small image. In order to do PLSA, you must run multiple.
Oh, this is PLSA on the tags, not PLSA on features. So this is like the classic PLSA with text, not the PLSA that people have used on image features. And so this is what we get when it works well. We're really able to separate out the different themes. And finally, we use Jan K's work on learning quality ranking from a database of images that have been ranked as being more professional versus more amateur. And the sole goal of that is just to find basically a nice looking representative for a cluster. Because, well, we could just use the image closest to the center or whatever, but somehow it seemed like a good idea to incorporate aesthetics more into the approach. So this is what the results look like for Apple. So each quadruple of images here represents a distinct theme found with PLSA and tags. And the different themes are laid out using multidimensional scaling. Multidimensional scaling using a distance between sets of tags. So it basically shows how close are these tag distributions to each other. So you can see we can separate the apple fruits very nicely from the Apple company. And we have nice distinct themes for logo, wallpaper, Apple stores. In fact, there's a theme for store in New York and store in London and so on. So you get the idea. So this is the top level. And we can expand. So this, for each theme, at the top level, we just show basically the 4 top iconic images, but there are more because there are basically several, in the intersection, there are several gist clusters that get intersected with the same theme cluster. So this, is all of the gist clusters that are under the same theme. And once again, as in the landmark work, we can expand a gist cluster to hopefully get a lot of images from the collection that are very similar, that basically support this gist cluster. So this kind of gives you the idea. Okay, so for beauty, what we have, once again, we have results that make a lot of sense. We have a cluster of different pictures of women. There's a theme, for some reason, for Japanese girls. And, we get flowers and sunsets and nature and cats. So this is an expansion of some of the women themes. So images here, so these are once again different gist clusters that fall under the same theme. So these are not supposed to be consistent in appearance. But if we expand a gist cluster, we expect images that are more consistent in appearance. But once again, the results we get here are not as clean as for landmarks, because in the landmarks, what really rescued us a lot was the 3D geometric verification. This is what helped us to clean up the clusters. And here, we have no geometry. We really have no additional cues to help us verify. So what we get in the gist cluster is really not as nice and clean a lot of times. Okay. But it works very well for flowers. And one thing that's interesting is we use no color at all. So gist is computed on gray level images, so appearance-based clustering does not use color. But in many cases, we find the results to be consistent in color anyway. So this is something that would be interesting to investigate. Basically, how dependent is color on global gist features and so on? How correlated is it? So a third category we tried is close-up. So this is even more abstract. It refers basically to photographic technique and not even to, any sort of concrete object or whatever, or any concrete subject matter. So basically here you get themes of what people like to take close-ups of. So they like to take close-ups of lips, eyes, cats' noses, insects, birds. There's a theme for more or less abstract macro shots, and we have a theme for strawberries. And also the drops of water, taking macro shots of drops of water seems to be very popular. So you can see this theme expanded, and this is a gist cluster for drops of water. This is one of the nice ones with the eyes. And one thing we can do, it's hard to really evaluate this in any quantitative way. It's hard to say how well we're doing. One thing I can point to is Flickr clusters. So Flickr clusters are, I think, computed solely based on correlations between tags. They don't use any visual information. But these are the kinds of clusters you get for close-up in the Flickr interface. So you can see, of course, there's not a lot of them. I think at most you only ever get 4 clusters in Flickr. And they're also not very satisfying. Like in the bottom cluster, cat and animal faces are mixed with people faces. In the top cluster, we get some objects and some insects. So in my opinion, the themes we get are kind of more satisfying. Everything is separated out a lot more nicely. And, our approach is basically very simple. It was our first sort of stab at how do we cluster these images. And, even just with PLSA clustering, we get, in my opinion, a lot nicer themes than what Flickr gets. So I guess the take-home message isn't really that we're doing so well. It's that, it's really, really easy to do better than this. Final one is love. So one surprise that was here, we have this cluster for self-portrait. So I was kind of surprised to see that as, a big theme associated with love. So I guess people love themselves, or I don't know, they love to take self-portraits. Then we get dogs and babies, which makes a lot of sense. What's interesting is that dogs show up under love and cats showed up under beauty. I don't know if this is just random or this really represents some big statistical bias in things. There's a cluster for wedding. A wedding theme, but the images in the wedding theme are actually not very good. So I'm not really sure why that is. And then, there's like cloud, sunset, beach. So beach and couples and love appear to be very tightly associated. It makes sense, but I guess I didn't really expect to see such a strong association. And there's a big heart cluster. Obviously, that's nice. If there wasn't a big heart cluster, then we'd know for sure that this thing has failed miserably. And one other thing that was interesting to see in this heart cluster, we get 5 images that basically are images of a ring laid on top of an open book, and the shadow of the ring is kind of heart-shaped. How many of you have seen these kind of images? So some of you have. Do you also browse Flickr a lot? Okay. So I think this is something that a lot of people are surprised who aren't familiar with Flickr and these kind of amateur photo sharing places. But I guess, this is one of these sort of visual cliches that people really love, and you wouldn't know it. So this was something I was pleased to see, because ideally this is, kind of output that I would hope from this approach. It would help to reveal these visual cliches that would, really be very prevalent, but, regular people might not necessarily know about them. So this is what I think would be really useful to reveal in a Flickr interface. And once again, Flickr clusters for love, not that great. So there is a cluster for hearts, but the heart images here are not particularly salient, although there's a better wedding cluster than what we have. But apart from that, once again, I think we do better in terms of comprehensiveness of themes and so on. Any questions? Yes?
So when you start doing your analysis, how many photos, or I guess it's based on retrieving a set of photos, right? So how many is the sort of starting set?
Oh, okay. So here it's smaller than for the landmark work. Here I think it's about 10 to 15,000 photos per category.
Okay.
So I think getting more photos would definitely be helpful for getting more consistent results. So here one of the shortcomings we have is we get sort of a set of themes that make sense. But it's hard to say basically, is this comprehensive? Are these all the important themes? Or or the themes that we do get, even if they make sense, how important are they? Like this self-portrait theme, it makes sense, but is this just a fluke of our clustering that it happened to reveal this theme, which might not actually be very common? Or is it indeed sort of a very common theme? And by contrast, you would think that weddings would be huge under love, but we don't get such good clusters for wedding. So the clustering is a bit iffy. So this is something that we really have to work on. Getting more data and implementing a more stable clustering algorithm where we would be able to say more things about, why did a given theme show up, why didn't it show up, and so on. Because this is hard to evaluate, one reasonable way to evaluate it is basically to do user studies, which would probably be a good idea. So that pretty much concludes my talk. Does anybody have any questions? Or, so sort of, oh, well. Yes?
Question. I'll ask them one at a time. One of them is, from the second half of the talk, it's clearly an amazing amount of information you can get out of these tags and the semantic information, but from a pure vision standpoint, it's a little unsatisfying in the first half of the talk that you actually need them to really filter your results. I was wondering, do you have any insights in, could you get away with getting just as good results using vision alone without the tags?
Yeah, so actually in our landmark work, we use tags for very little. So the only thing we used them for was filtering the isolated nodes of the graph. So the clusters that didn't match any other clusters geometrically. So we apply the tags in the first part of the work after we've already applied all the stronger constraints that we have. And basically the only thing that would happen if we didn't apply that step would be we would end up with more sort of garbage components. Like here I can show for Notre Dame, I'll show you one example of sort of a garbage component. So for Notre Dame, we have this component that is geometrically consistent because they're all images of the same building. But it's obviously not the Notre Dame Cathedral in Paris. Tags in this case don't give us enough information, once again, to remove this because it's tagged with Notre Dame and art, which are both very common for the correct Notre Dame. So basically, if we used no tags at all for this step, we would simply end up with more garbage components like this. So we really don't rely on tags for a whole lot for the landmarks. And for the second part of the work, we rely on tags because semantics are much more important, and because we don't have strong constraints. So geometry, basically when geometry makes sense, whether 2D geometry, appearance similarity, or 3D geometry, it's really good to use it. But here, for general categories, we're basically in a situation where we have very little to go on, so we're forced to rely on tags.
Okay, my other question relates to that San Marco example where you couldn't glue the two halves of the plaza together. And it's a very common problem in these feature-based approaches that when you have repetitive structures, that you could get confused. And I can kind of see two approaches to handle this. One of them would be to do more verification. There might be some asymmetry that you could leverage and say those are actually two different views of almost the same thing. The other approach would be to have like a particle filter type approach where you say, well, here's multiple hypotheses and I need to carry them all around. You have any insights how you could use either one of these approaches?
So I think you could in fact use both. So we've talked about it a little bit. So, I think being able to generate multiple hypotheses, especially in the tower case, there's really basically a fourfold ambiguity. So it's really not that hard to keep track of it. So it may be simply just a question of re-implementing your ransack, where instead of just spitting out one hypothesis, it kind of, it spits out all of the sort of consistent hypotheses. So you can, if there's just a fourfold ambiguity, then you can keep track of it pretty easily. But also in that square, where, the back of the square where you have these repeating columns, the ambiguity might be a lot bigger. When you have this, translational ambiguity, you might have a lot more than 4 possible hypotheses, so it could blow up. So it's a question of, where do you want to stop? And, it's also a question, I guess, of careful implementation and so on. So I think just carefully keeping track of the ambiguities and generating multiple hypotheses, in some cases when there's just a 2-fold or 4-fold symmetry is all that's needed. But in some other cases, same with particle filtering, it might blow up when there's just too much symmetry. But yeah, I think especially in architectural scenes, dealing with symmetry is important. And the first thing you mentioned, obviously getting more matches, trying to, get some unique features, I think also is part of the solution. So it could be as simple as just, more carefully implementing the SIFT-based matching and extraction, using higher resolution images and so on. So I think part of the answer is, more careful implementation, and part of the answer is, there are probably issues that we don't even want to touch, when some of these basically ambiguities get out of hand.
Other questions? Okay, so Lana is here for today. If anyone would like to meet with her, just come and see me. We're probably just going to go out for lunch in the cafeteria here if anyone wants to join us for lunch. So thank you once again.